So we left off talking about the bright line spectrum of different elements, and we started viewing them in class with the gas discharge tubes. And we know that these bright line spectrum were around for many, many years before they were actually explained. There was a bunch of different people that were working on what they were, or at least how to use them. And they knew early on that this light that was essentially broken down into individual wavelengths from the raw light given from elements that are being excited somehow was a actual footprint. They knew that each element had an individual light associated with them when they got excited or when they were given energy. They didn't know any more than that. And it was a phenomenon, just like the photoelectric effect was a phenomenon, or the cathode ray tube was a phenomenon, and there were people working on it. So the people that were actually um, uh, working on this phenomenon were Anders Johannes Angstrom. That's where the angstrom unit came from, and David Alter, Gustav Kirchhoff, Robert Bunsen were all people that were working toward the technique of trying to break the light into individual bright line spectra and analyzing them. Now, the there was so much, as we've seen already, that is complex about the emission spectra. I've seen plenty of examples. The one that I just showed you, um, neon, for instance, uh, very, very complex. Some are thick and thin lines, and look at this helium with a dark yellow line that I'm going to show you, or I have shown you in class already. Very difficult to explain a multi-electron system, and that was not something they were trying to do. So they were actually starting with the most simplest, and of course, that was, of course, hydrogen. And essentially, Balmer was coming up with a formula in 1885 to explain the energy of hydrogen spectra. Again, it was the most simplest, one proton, one electron, using a formula he put together. Now, certainly, Planck's constant and these numbers here were something he did not know what they were. They were whole number integers, but it certainly worked out in figuring out the wavelength, the known wavelengths of these lights. So somehow he was figuring out the wavelength of what these lights, individual wavelengths were, and they knew that from how they diffracted through a lens, but they did not know what it meant in the atom. So certainly early work was going on. Now Niels Bohr took Balmer's equation for this wavelength and adjusted it for photons of light from Einstein, and he made up his very famous equation here that the energy of an integer, some integer, is negative 2.178 times 10 to the negative 18 joules over this n number squared. Okay, as I talked about in class, this is an inverse square law. And this actual number here is the binding energy of an electron to the nucleus in a first energy level. So what Niels Bohr did was he took the Balmer equation and adjusted for it based on energy per photon that we talked about that Einstein did, and he adjusted it for whole number n's. And what was revolutionary was this n was actually, he called shells of electrons. Now again, don't forget this is for hydrogen only. All right, so he was able to look at the energy of each individual shell or orbit from the nucleus. All right, in any case, he suggested that electrons in an atom were quantized, had discrete energy levels, and these were the energy levels of each of these individual energy shells. So if you look at the Bohr's planetary model, the n equals 1, n equals 2, n equals 3 represented the essentially the major energy levels that electrons can only have, and they existed in particular distances from the nucleus. So this n number, as I'm showing you in the Balmer equation, which I keep calling, but it was adjusted by Bohr, shows you the energy of each of these shells. What was really fascinating was that this energy level that he calculated with these individual shells here, when you subtracted the energy levels, let's say an electron was going from, let's take it 1, 2, 3 to 4, okay? That would be that green line. I think this 3 to 4, I'm sorry, is that red line, the Balmer series. Oh, I'm sorry, 3 to 2 is the red line in the Balmer series. So if we go from 3 to 2, we know it's the red line. And we know it's the red line because we can take the energy per photon of a red photon in that wavelength, and what we can do is we can take the energy of the third shell, putting a 3 squared here, putting this negative number on top, and we can get the energy of the third shell, and then we can get the energy of the second shell by putting a 2 here, and by subtracting those values, it comes out to exactly the energy of that photon. And that's really essentially where he won his Nobel Prize. So if we look at his emission bright line spectrum of hydrogen, you can see the 3 to 2 transition gives off a certain measured, and they can measure this, and this was not difficult to measure, but again, that was the work of the bunch of scientists, the Kirchhoff, the Bunsen's, okay, the angstroms. They measure these wavelengths of light, and knowing the wavelength of light, and now of course knowing that energy equals Planck's constant times the frequency, getting a frequency, they know the energy of this photon of light, and of course it matched the difference in the energy of the third energy level, which we do by plugging the 3 in here from the 2. And again, this is an inverse square law. So if I know the energy that it takes for the first energy level, or know how much energy it takes to pull an electron away from the first energy level, that's essentially what this number is. As we go farther away, we can see that that number is going to get certainly smaller, because this number is being squared. And that's the reason why these leaps are big, and we talked about that as an inverse square law. All right, and you can see these numbers. In fact, the inverse square law, really, essentially, that he's building in here is really due to something called Coulomb's law, which is force is equal to some constant times 2 charges over the radius squared. Again, an inverse square law. So as you get farther away, you double the distance, you quarter your attraction to the nucleus. And same thing here, we triple the distance, or we go to an n equals 3, and now our attraction is 1/9 of what it was. This is 4th, 1/16, and so forth. And that's why the energy levels, as we looked at, get closer and closer together. And the other way to look at it too is that there is a finite distance. Electrons cannot exist infinite distance from the nuclei. So eventually, there has to be some limit to how far the electrons can exist, and of course that's a nice way of thinking of it, why it kind of approaches each other. There has to be some limit, because after a while you gain enough energy, the electron of course becomes free. All right, and in any case, something else to think about as I go back here is that you notice these are negative energies. So they consider the system, they consider an electron by itself to have 0 energy. So as it goes back toward the nucleus, it loses energy, okay, to get closer to the nucleus. As it loses energy, as it gets closer to the nucleus, that's why these numbers are negative. So that's the system they use. Electron having no energy when it's free from the nucleus, and this is how much it loses. So it's kind of a weird system. It's losing something that it doesn't have, okay, but that's the way they've always thought about it. So the negative 21.56 shows you how much it's lost to get this close to the nucleus. And it has to lose energy, because if it has energy, it'd be able to pull away from the positive nucleus of the atom. Always think of the nucleus, okay, right here in these types of equations. All right. In any case, you can see the inverse square law at work. This number is a 4th of this number. This number is a 9th of this number, a 16th of this number, and that's because, again, of this n squared, which is really tied to the attractions of the positive to the negative. So you'll hear in your discussions the Coulombic attractions. It's about positive attracting negatives. All right. So he tied that all nicely together, and of course he was very, very, very how can I say, successful in explaining the hydrogen emission spectrum, these lines. So let's take that information and take the Balmer equation, which by the way is given to us in our reference tables. And there it is. Atomic structure is right here. Here's our atomic structure formulas, and here is the Balmer equation. Negative 2.178 times 10 to the negative 18 joules over this n squared. This n squared is basically which shell we're talking about, 1 through 7. Now, what I'd like us to do is go to the atomic structure worksheet that I gave you too. That's the Bohr model, and we're going to go on the back side. The first side we should have completed. Okay, so here we are, atomic structure 2. We're going to go on to the back side. This is something you should already have. We should have already worked out these very simple equations by using our couple of different formulas. And now we're going to go to the back side. It looks like a little more of a diagram that we've been working on through the the notes of the presentation. And this is another diagram to show the different types of transitions in the hydrogen atom as worked out by the Bohr. Now you'll notice there's something called the Balmer series, the Paschen series, the Paschkin series, the Lyman series, and these are just different people who work particularly in the areas of hydrogen in the different spectra. Infrared, the short leaps, and of course the long leaps or the ultraviolet. We're dealing with the Balmer equation, essentially that what Niels Bohr worked out in terms of the parts of the spectrum that we can actually see, the light spectrum. Okay, so in any case, what I want to do with this was just a very simple exercise. I want to kind of put the Balmer equation to work. Okay, and if you remember, the Balmer equation is nothing more than this number, okay, over n squared, and that equals E of that n, that shell. So what I want to do is I want to figure out how much energy does a hydrogen atom lose when its electrons change from the fourth energy state to the second. Okay. Now, before I do that question, I kind of want to investigate this line right here. Okay, I want to look at this line, and I want to do that right here. So, if we were to measure in a laboratory 656.5 nanometers, how does that represent the energy levels that or solved for by the Balmer equation? All these numbers are solved for. Okay, like if I was to put a 2 in here, that would give me this number. If I put a 3 in here, this is the exact energy level for the third. So if I use this Balmer equation, I can come up with these values. So essentially, if I want the energy of the fourth energy level, negative 2.18 times 10 negative 18 over 4 squared would give me this number. And that's the energy in joules that electrons would have to get to the fourth energy level. Or at least that's the energy, that's the energy of the fourth energy level. The energy that electrons have to get exactly from a photon to go from 3 to 2 is the difference of these two. Okay, and we'll get to that. So in any case, let's go investigate the third, that red line, first of all, okay, before we do the actual question. Okay, so we have some governing equations here. We have energy equals Planck's constant times frequency. We also have speed of light equals wavelength times frequency. Okay, now to figure out the actual energy, we need a frequency, but we have a wavelength. Now, one way to do this is understand that a wavelength, okay, is equal to a lambda. Well, in this case, we're going to look to combine these two formulas. So if I combine these two formulas, let's solve for frequency. Frequency from this formula, okay, is equal to C over lambda. Now, if I know that, and as I've talked about this before, C over lambda, okay, will be plugged in for the V, and what will that'll give me an energy, I'm just going to do this up here now, is equal to H, Planck's constant, times the frequency, which equals this. So we have C over lambda. Okay, so all I got to do is plug in the two constants and divide it by the wavelength. Now the wavelength's in nanometers. Okay, Planck's constant is in joule seconds, and speed of light is in meters per second. So the meter per second won't cancel with the nanometers to get my joules, right? Joule seconds, meter per second, and the meter here, it just won't cancel. So I'm going to have to convert this to meters. So very simple, something we should be able to do. 656.5 nanometers. I'm going to get rid of nanometers, so nanometers go on the bottom of my conversion. And of course, I am going to want meters, and I know 1 meter is 10 to the 6th. Up 10 to the 9, it's a billion. Nanometers cancel, and what I have here is 6.565 times 10 to the negative 7, and that of course is meters, and that's my wavelength. Okay, now all I got to do is plug into my formula, and energy is equal to Planck's constant. So 6.62 times 10 negative 3 joules seconds. That's my Planck's constant. And of course, speed of light, we can round off 3.00 times 10 to the negative 8 meters per second. And then, of course, that's all over my wavelength, 6.565 times 10 to the negative 7 meters. Let's go find that number, but cool, if you look at the units, make sure they cancel. You notice possibly that my meter will cancel. That's what we had to be in meters. And of course my second cancels here and I'm left with joules. Okay, looking over this, I see that this should be a regular 8. Speed of light is a big number, greater than 1, so that's a positive 8. So I get a rounded number of 3.025. Actually, that's not rounded now, it's going to be rounded. Let's 3.03 I should probably put. 3 significant figures. 3.03 times 10 to the negative 19. Of course, we're in joules. That's a 19. And that is my energy of the red photon. Now, what I want to show is that that should be the difference between the second and third, or I'm sorry, the third and the second, same thing, I guess, energy levels. So if we're saying the red photon came from, okay, this leap right here, then this energy difference has to be the difference in his equation. So if you look at his equation, and by the way, these numbers come from his very simple Balmer equation, not that simple, I guess, this divided. So this number came from taking this number and dividing by, this is the second energy n squared, so it's a fourth of that number. So subtract these two numbers. Now, since they're both 10 to the 19, okay, it's just subtracting 5.54 and 2.42. So you put that in the calculator, 5.45 minus 2.42, and you get 3.3. Which we got 3.03, of course, times 10 to the negative 19. Okay, and of course that is the difference in energy between his energy levels, and that is exactly the energy of a photon. So when he matched his equation and the energy levels and the difference between those two to the energy of the photon, that is what caught everyone by surprise. That light matched energy levels that are exactly held in an atom. All right. Now, the other question here, how much energy does a hydrogen atom lose when its electron changes from the fourth energy state to the second? What is the wavelength of the photon emitted? Okay, well, I'm going to get rid of this information here. Let's do this question. Now, we're going to do this question without knowing what the energy levels are and just be given the Balmer equation that's given to us in our reference table. So the Balmer equation is e to the n is equal to that negative 2.18 times 10 to the negative 18, okay, over n squared, and that's of course joules. Okay, now he wants to know the energy hydrogen atom when it goes from the fourth to the second. All right, so that's the leap going to go from 4 to 2. So we're talking about this leap right here, which by the way would be this line right here. Any case, not knowing the energies, just given the formulas, we have to know the energy of the individual. So let's do the energy of the fourth. So the energy of the fourth energy level would be this negative 2.18 times 10 to the negative 18 joules over, well, 4 squared is 16. So let's go find that. So put that in your calculator, negative 2.18. Second function to the negative 18, okay, divided by 16. This is the fourth energy level. So I get the energy of the fourth energy level to be negative 1.36 times 10 to the 19. So that, of course, is the energy of the fourth. Okay. Now the energy of the, let's do the energy of the second will be equal to the same number divided by 4. So 2.18 times 10 to the negative 18 joules divided by 2 squared, which would be 4, right? Because it's the second energy level, so 2 squared is 4. So, I mean, I know that we can do it from that number, but let's just start from scratch. Negative 2.18. Second function I do on my calculator to the negative 18. And divided by 4. And I get, of course, the energy of the second equal to negative 5.45 times 10 to the negative 19 joules. And that is my energy of the fourth. This is the energy, energy of the second. This is the fourth. So what's the energy difference? Okay, well, you subtract them. So when you subtract those two numbers, and you say, my gosh, these negatives, these positives, okay, I make my life simple. I'm just going to do 5.45 minus 1.36. But you can do, if you want to, negative 1.36 minus negative 5.45. Okay, and what you'll get is 4.09. Okay, so we subtracted those two numbers. We got the difference of the difference in energy of those two values, and I get 4.09. Okay, of course it's times 10 to the negative 19 joules. Okay, and that's the difference between the fourth and the second. This is the energy of the second, and that's the energy. Now, how much energy does the hydrogen atom lose? So a hydrogen atom loses this energy, 4.09, when it jumps from the fourth to the second. So here's the nucleus. Here's the first, second, third, and fourth. So from n equals 4 to n equals 2, that's how much energy it loses, 4.09. Now you want to know what's the wavelength of the photon emitted. Well, if I know the energy is equal to hc over lambda, I can rearrange this and say that lambda is equal to hc over the energy. Okay, so I have the energy, and now I take Planck's constant, which is the 6.62 times 10 to the negative 34 joules seconds, times it by the speed of light, 3.00 times 10 to the 8 meters per second. Not really being very careful with my spacing here, but we can do this, noticing that the joules are going to cancel, okay, and the seconds will cancel, and we're left with meters. That makes sense to us because we're solving for a wavelength. So let's plug this in. Okay, and so what I get is 4.86 times 10 to the negative 7 meters. And that's the wavelength of the energy, or of the photon, that would be emitted if electron jumped from the fourth, to the second energy level. Okay, and if you look very carefully, does that correspond to the actual measured wavelength of that line? And it does. 486.1 nanometers is the same thing as 4.86 times 10 negative 7. So if you converted this into nanometers, that'd be the same number. Okay, so that is how that works. So yeah, our number works perfectly. And again, he was able to, very, very accurately explain these spectral lines in terms of leaps of energies from the equation he developed. Okay, so very, very nice equation that worked really only for hydrogen, but it showed, at least in his idea, that the electrons in an atom are quantized. So you're responsible for knowing how to do this Balmer equation. Okay, and what I'd like you to do is take out Atomic Structure 3 worksheet that I gave you Friday, that's also posted, and I would like you to do just questions 1 and 2. The key is posted. Now, number 1, just to help you understand what we're doing here, in number 1, what you're going to do is you're going to figure out the energy of the difference of energy. So if we're going to absorb a certain amount of energy, so the X-ray of a helium atom, so you notice energy is going to be absorbed, okay, and they're saying the X-ray absorbed a wavelength of 53.7. So that's a wavelength. You've got to convert that to an energy, so you can assume that all that energy went to a certain state. So whatever it absorbed is now there. So this is the energy here, and now it says it emits a wavelength, okay, of 506. What energy is representative of that? So essentially, I'm looking for the difference of those two states there. So if you didn't quite get there, but I want to see an energy diagram. You got to convert these wavelengths to energy like we did. And number two, just a little quickly, calculate the wavelengths that hydrogen emits that atoms in the fifth energy levels can emit. Now, if you're in the fifth energy level, here's the nucleus. Here's 1, 2, 3, 4, and 5. Certainly, it's drawn probably better than that, but with the inverse square. But in any case, so if we're talking about what kind of wavelengths can the hydrogen atoms emit, well, we can go to what? 5 to 4, 5 to 3, 5 to 2, 5 to 1. Okay, those are the different types of things. So I'm looking for 5 to 4, 5 to 3, 5 to 2, 5 to 1. So I'm looking for those different leaps, okay, or those quantum leaps, those energetic differences there. And of course, I'm calculating the wavelengths there. So please, that one's going to need the Balmer equation that we talked about. So 1 and 2 is your homework. Okay, thanks.